In this video, we will be learning about molarity. The learning objective for this video is calculate concentrations of solutions that involve molarity. So we learned earlier that solutions are homogeneous mixtures. With any mixture, the composition can vary from one substance or from one sample to another. And so the difference between these two samples here is that one sample is more concentrated than the other. Both have the same mass of copper nitrate dissolved. What's different about these two samples is the amount of solvent. And so you can see that the color is a lot brighter here, and that's because it's more concentrated. There's more copper nitrate, or the same amount of copper nitrate in just a less volume. If I was going to add more solvent to this, then the color would get lighter, much like it has in this one, because those copper nitrate particles are more spread out. A lot of times when we prepare solutions, we have to start with a mass of a solid. And so we take some solid, we weigh it out on a balance, and then we add it to a flask, add some solvent, swirl, mix, make a solution. And we learned earlier how to convert between the unit of grams and moles. And so this tool here was our molar mass. We use molar mass as our tool whenever we're trying to go from a solid mass to the mole unit. Once we make a solution, a lot of times the solution's concentration is reported in a unit called molarity, which is given a small caps M for a unit symbol. So the definition of molarity is moles of solute, which you'll remember is what's dissolved. What is dissolved per liter of solution. Solution is the entire mixture. So for example, this problem says calculate the molarity of 275 milliliters of a solution that contains 1.10 moles of sodium chloride. So this is my solute, and so that's going to go in the numerator for my molarity. So molarity is going to be equal to my 1.10 moles of NaCl, and then this is reported in milliliters, but the definition of molarity is per liter, and so I have to convert this to liters. And so to convert to liters, I have to divide by 1,000. And so 275 milliliters is 0.25 liters. There are 1,000 milliliters in a liter. So I can calculate the molarity by typing this into my calculator. And I end up with 4. Well, it just says 4. Now I have to think about sig figs. This number had 3 sig figs, this number had 3 sig figs, and so I have to make my answer have 3 sig figs. That means I have to add back on some significant zeros and then put my unit afterwards. And I can either write the M for molarity or I can write moles per liter. Whichever you prefer. I will treat them the same. When we read that output, it's not read 4.00 M, it's read 4.00 molar. So like the back teeth in your mouth are molars. That's how we pronounce that word. Molarity is a very useful unit because it can be used as a conversion factor whenever we're trying to go from liters of a solution into moles of my solute. So whenever you're trying to go between the units of liters and moles, and you have liters of solution and moles of solute, you will be using molarity as a conversion factor. So just as a review, or to distinguish it from density, like if you had liters of, if you had like a volume of your solute and you're trying to go to grams of your solute, then you would use density as your conversion factor to do that unit conversion, because both of those are, so for density you have to have the volume that corresponds to that mass for the same substance. So you could either have liters of solution and grams of the same solution, or grams of solute and liters of solute. But the thing is, it has to match. This is going from solution to solute. So like here, it's not necessarily the same exact thing on both sides. And that's what makes it very useful. Here's an example of molarity being used as a conversion factor. This problem reads, what is the mass of NaCl required to make 275 milliliters of a 2.25 molar solution? And so whenever I see concentration given to me, I have to think to myself, this must be a conversion factor. And so a lot of times it's easier to see it as a conversion factor if we don't write the M, and then we instead write moles per liter. Because if I want to keep that 2.25 to have a value of 2.25, I can just divide it by 1. Anything divided by itself or divided by 1 is itself. So now I can rewrite that so it looks like my conversion factor, and now I can think of what I'm going from and to. And so I am given 275 milliliters of a solution where NaCl must be my solute. And so I am asked to find mass. It doesn't tell me a particular unit of mass, so I'm just going to go with grams. That's like my default mass unit. Grams of NaCl, which must be my solute. So my map, my solution map, I know I'm going to have to use my density as conversion factor. That's going to require liters though. And so I'm going to have to go from the milliliters I'm given into liters so that I can use my molarity as a conversion factor. Then if I'm using molarity as my conversion factor, that will point me into moles of NaCl. And it's asking me for grams. And so once I'm in moles of NaCl, I'm trying to get to grams of NaCl. I go from moles to grams using the molar mass of NaCl. So I'm going to need to calculate that. So I'm going to start with my 275 milliliters of solution, convert to liters, and so there are 1,000 milliliters in 1 liter. Then I'm going to use my molarity. I have to cancel out my liters and I have to go to moles. So the 2.25 is attached to the mole. 2.25 moles per 1 liter. And that's of sodium chloride. And next I'm going to have to cancel out my moles of NaCl and go into grams of NaCl. So that means I'm going to need my molar mass of NaCl. Whenever I use molar mass, there's a 1 next to the mole. So let's go ahead and calculate that. If you want to pull out your periodic tables, you can. And so the molar mass of sodium is 22.99. And then there's 1 chlorine, which is 35.45. And so my molar mass of sodium chloride is 58.44. So now I can calculate now that I got everything set up, I can plug this into my calculator. And I'm just going to set it up so that it looks exactly like what's on my paper to make sure that I am communicating with my calculator exactly what I meant to. There, it looks exactly like what's on my paper. And so this works out to 36.15975 grams. I'm going to need 1, 2, 3 sig figs, and then this also had 3 sig figs. So I'm going to need 1, 2, 3 sig figs, and so this is going to round to 36.2 grams. Come on, go to the next, no. Yep, 36.2 grams. All right, here is a practice problem for you. It reads, how many milliliters of a 4.00 molar NaCl solution would contain 1.16 moles of NaCl? Go ahead and pause the video and try to work that out on your paper in your notebook, and unpause the video when you are ready to continue. Okay, let's go over this. So I got my calculator ready. We are asked to find mLs of solution. NaCl is like an adjective here that's telling us our solute in the solution. And we are given 1.16. And that's my solute. I am told the concentration. That must be a conversion factor. And I know that the M really stands for moles per liter. So I'm looking at my units here, and I'm definitely going to need that to go from moles to liters. So I'm given moles. Molarity will get me to liters, and then I'll have to find milliliters from that. So 1.16 moles of NaCl, and then my molarity, I have to cancel out moles, and I have to get into liters. So that 4.00 has to go in the denominator so that my mole units cancel. And then the 1 goes next to the liter. Next up, I have to cancel out my liters, and I have to get into milliliters. And so I have 1,000 milliliters in 1 liter. So if I clear my calculator, I have 1.16 times 1 over 4, and then times 1,000 over 1. And so that tells me 290. This has 1, 2, 3 sig figs, 3 sig figs. And so my answer has to have 3 sig figs. So I have to make sure that I put a dot there to make sure that 0 is significant. So I will need 290 milliliters of the solution. Here's another practice problem for you. It reads, what is the molarity of a solution containing 3.4 grams of ammonia? And then it gives us grams per mole of ammonia being 17.03. And then it says in 200 milliliters of solution. Go ahead and pause the video and try to work out this problem on your own. Unpause the video when you are ready. Okay, so we are asked to find molarity. And I know the units of molarity are moles per liter, moles of solute per liter of solution. So I am not given moles of solute, instead I am given grams of solute. So I am going to have to, I am given 3.4 grams of NH3. I am given volume also. So at least I'm given the liters of solution. I'm given it in milliliters, but I'm going to have to convert this into moles. And I'm going to use the molar mass in order to do that. The molar mass is given to me, and we know that's the molar mass because of the unit. The unit is grams per mole, which matches the unit of molar mass. So I can use my molar mass to go from grams to moles, and that will give me my numerator, and then I can just divide by the molarity or divide by the volume in order to get molarity. So my numerator is going to be 3.4 grams, and then I'm going to cancel out my grams by dividing by the molar mass. So 3.4 divided by 17.03 is 0.19964. My volume I have to get into liters. And so I have practiced this enough that I know to go from milliliters to liters, I have to divide by 1,000. And so that will be 200.0 liters. So 0.2 with 3 significant zeros afterwards. All those zeros were significant. And so I'm going to divide both sides by the volume, because if I divide one side of the equation by the volume, then I have to do the same thing to both sides of the equation. And so now this is molarity, that is molarity. So now I have to divide by 0.2000. And that gives me 0.99823 molar. How many sig figs do I need? That is 2 sig figs in my mass. So that's going to limit my sig figs to just 2. So the 8's going to round up. That's going to make that a 10, which is going to carry over and make that a 10, which is going to carry over and give me 1.0 molar. Before we continue, we should do a conceptual check. Think back to your electrolyte strength video and try to identify which picture best represents calcium nitrate aqueous. Pause the video if you need to have more time to think. All right, so calcium nitrate is an ionic compound. Ionic compounds are strong electrolytes. Strong electrolytes separate into separate cations and anions. This had the example on that particular side had hydroxide. This is nitrate though. And so we have NO3 minus as our anion. The chemical formula here though had a 2. And so that 2 is going to come out in front and tell us that we have 2 separate nitrate ions for every 1 calcium. And so we need a picture that has nitrates intact. So both of A and D do not have nitrates intact. So neither of those have NO3 ions. B is going to be our correct answer though, because it has twice as many nitrates as it does calcium. So this has the right ratio of calcium to nitrate. This one is missing nitrate. So that conceptual checkpoint was to help us with this type of problem. Strong electrolytes dissociate into separate ions in solution. So the molarity of individual ions will depend on how many of each ion there was in the original compound. So for instance, let's say that this was a 2.5 molar calcium nitrate solution. If we were going to figure out the ratio of the individual ions, then we can take our moles per, we'll just do moles of calcium nitrate, that's moles per liter, and I can cancel out moles of calcium nitrate and just end up with my nitrate. That subscript 2 can come around and become a coefficient. So using the subscripts as a conversion factor here. And so that tells us that our molarity of nitrate ion is going to be 5.0 molar. And so I can do the same thing. You see that the moles cancels out, but then I'm left with moles per liter. And so my final unit is still molarity. If I do the same for the calcium ion, then my coefficient is just 1. So my molarity of calcium ion will be the same as my molarity of the whole compound. And that was for the nitrate. So here's a practice problem for you. It reads, which of the following solutions has the highest concentration of hydroxide ion? Pause the video and try to think about this. Unpause the video when you are ready to check your answer. Okay, so let's look at whether they are strong or weak electrolytes first before we get started. Calcium hydroxide is a strong base and it's also ionic. And so that's ionic. This one is also ionic. This one though, it's non-ionic. This is molecular. It's an organic molecule. That's methanol. We'll learn about nomenclature for that soon. So molecular compounds are non-electrolytes. Non-electrolytes have no ions. So that will not come off in solution. So we can just cross that out right now. Now we have our third one as ionic. So now looking at the remaining answer choices, we have 2.5 molar calcium hydroxide, which is going to have 2 hydroxide ions for every one of the compounds. So that's really 5.0 molar OH minus. B has 4.0 molar of the compound, but there's only 1 ion, so it's the same, 4.0 molar hydroxide. And then that one's just 2.0 molar. So our correct answer is A. A will have a 5.0 molar hydroxide ion concentration.